Hello everyone, today we'll be discussing how to identify a redox reaction using the two definitions of transferring electrons and transferring oxygen. A compound that loses electrons is oxidized, and a compound that gains the electron is reduced. So you notice redox is made up of two parts. So it's made up of a reduction half and an oxidation half. So the oxidation half stems from the compound that loses the electron, and the reduction half is when the compound gains the electron. So there always needs to be two parts. So the reason for that is that an electron can't just disappear. It always has to be one given and then two accepted. So you will never find just a reduction or just an oxidation reaction. They are always one half of a process, so you always find both. A little memory trick we can use to remember this is that oxidation is the loss of electrons and reduction is the gain of electrons. So we can see here that compound A has lost the electron to B, so it starts with the electron and then loses the electron. So A is oxidized, we will say compound A has been oxidized, and compound B has gained the electron, so we would say compound B has been reduced. So now we're going to look at an example of a redox reaction. So I'm just going to give this one to you guys. We can see that the hydrogen has reacted with chlorine gas to give hydrochloric acid. So we know this is a redox reaction because when we split the reaction into two, we need to take all parts with us. So any part that's been chemically changed, we need to assign it in terms of a half reaction. So we can see that the hydrogen needs to be as a reactant in one half equation, and then we've got hydrogen as part of this hydrochloric acid. So the hydrogen in part of the hydrochloric acid is actually a hydrogen ions, so actually acid. So we obtain these two reactants and products all from our full equation that we're given. We don't have to generate any extra chemical parts. The one part that we do have to do ourselves or add ourselves is when we have to balance for charge. So that's our step 2. We balance for charge by adding negative electrons. Each electron is assigned a full negative charge, single negative charge, and we always add it to the more positive side because we can't add more positives to a negative side. We always can only add a single negative. So we can see that hydrogen gas is neutral in charge, and then the two hydrogen ions each have a single positive charge. Okay, so overall it has a 2 positive charge, and we need 2 whole negative charges to cancel out the 2 positives, because overall we need a charge of 0. So they each need a charge of 0. So 2 plus negative 2 is equal to 0. Okay. And we can see that the next half reaction, we have chlorine from our chlorine gas going to chloride in the hydrochloric acid. So we can see that we have a neutral chlorine stemming straight from our full equation. Then we have the chloride coming from our hydrochloric acid, and there's 2 chlorine atoms present. So all we need to do then is balance for charge by adding electrons, and we can see that we have a neutral chlorine, so 0, and 2 lots of negative 1, and overall we have negative 2 on the right hand side. So to balance, we just need a negative 2 charge on the left hand side, and we are complete. We have our 2 half reactions, redox half reactions, and we can see that we have our oxidation half reaction stemming from our acronym we learnt before, oil rig. Oxidation is loss of electrons, and we can see it's a loss of electrons because we have our electrons on the product side of the equation. So they were generated from a half reaction, they were given away. Let's think of it like that. So when they're on the product side, the electrons are given away, they are lost. As in when we have the electrons on our left hand side, our reactants side, we are consuming 2 electrons. So the chlorine gas is effectively consuming 2 electrons from the hydrogen atom or molecule. So they are accepted to form the 2 halide anions. So we would call that a reduction half equation, gain of electrons. Okay, so we've gone through one whole example. Now have a go at the example now given here. So pause the video, use our steps that we learnt before and attempt to write down the 2 half equations. Okay, so we can see that we've got a zinc species on the left hand side and a zinc 2+ ions on the right hand side. So we can see that we have neutral zinc on the left hand side and then a zinc +2 charge on the right hand side. So overall we have +2 charge on the zinc and 0 on the zinc metal on our left hand side. So to balance we need a 2 charge from 2 lots of a single negative electron charge. And the second half equation comes from our copper ions reacting to form copper metal. So once again we have a +2 charge on our copper ions and a neutral charge on our copper metal. So to balance we need to once again add 2 electrons to our more positive side. We are always adding our electrons to the more positive side of our half equations. So now that we have our half equations, we need to assign a oxidation half reaction label and a reduction half equation label. So we can see that the loss of electrons from the zinc, so oil rig, oxidation is loss of electrons, so we would say zinc has been oxidized. Whereas copper has gained 2 electrons, so copper 2 will be the species being reduced. So now we've got magnesium reacting with diatomic oxygen, the oxygen that we breathe in the air, to form magnesium oxide. So once again we have to first identify the reactant and product in each half equation. So please pause the video again and have an attempt, and then we'll go through the answer together. Okay, so once again we are trying to pick out our reactant and product. So I can see I've got magnesium on the left hand side and then magnesium on the right hand side in that salt. So we know it's a salt because we have a positive component with our magnesium and a negative component of our oxygen. Very similar to our sodium chloride. Okay, so the half equation for the magnesium is 2 lots of magnesium, so I'm just going to carry that to the half equation, reacting to form our 2 lots of magnesium positive ions, and to balance we need 4 electrons. Now we know that because we have 2 lots of 2 positive ions, so overall we have a charge of 4+. And so we need a charge of -4 to counteract that to give us a charge of 0, because these 2 need to be equal. Okay, next is the oxygen. So the oxygen, interestingly, is written as a single oxygen from our salt, and we assign it a -2 charge. So we just carry the charge of what we would find in the salt, and this all stems from oxygen being in our group 6 on our periodic table, whereas magnesium will be in our group 2 and only has a 2+ charge. So we just carry that charge, same with the magnesium and same with the oxygen, along in our half reactions. So overall we have a neutral diatomic oxygen and 2 lots of a -2 oxygen ion. So overall we have a -4 oxygen species charge on our right hand side from our oxygen species, so we need a -4 charge added in terms of 4 electrons on our reactant side of our half equation. So once again we need to label using oxidation and reduction. So the half reaction losing electrons, so on our right hand side, our product side, will always be our oxidation half reaction, and the electrons on our left hand side will be the half reaction, that is the reduction half reaction. So the second definition we're going to practice with now is the transfer of oxygen redox definition. So with our acids in our sort of later years in high school, we have our single Bronsted acid definition where we lose or gain hydrogen ions. So a lot different to that is that redox can have multiple definitions. And at any moment, we can use multiple definitions to obtain the same result. We will always obtain the same result. So we're going to have a look at the magnesium and oxygen reaction once again, but we're going to use this new definition now to see if we come up with the same solution. So our definition states that redox reactions involve a transfer of electron between two chemical species, so just between two molecules. The compound gaining the oxygen is being oxidized, so that makes sense. We're adding oxygen, so it is being oxidized. So that's a good memory trip. Oxy is oxidized, so gain of oxygen is being, so therefore it is oxidized. And we need a reduction component because it's Redox, and we just say the compound losing the oxygen is being reduced. So often it's easier to start with the compound without oxygen. So I'm going to start with our magnesium. So it has no oxygen attached to it, then is reacting with diatomic oxygen to form magnesium oxide. So in a sense, the magnesium has gained oxygen through this reaction. So since magnesium has gained oxygen, we would say that magnesium has been oxidized. And therefore, since we have we'll need a full redox reaction, we need the reduction half of this reaction. So the oxygen species itself lost oxygen when it combined to form magnesium oxide. So we say diatomic oxygen has been reduced. So we're going to look at a different example now involving two species that aren't diatomic oxygen. So pause the video, use the definition, and try and attempt to label the molecule that is being oxidized and the molecule that is being reduced. Okay, so we can see that iron oxide has the oxygen to begin with, and the carbon species, pure carbon, starts without the oxygen. So we're going to start with the carbon, as always, and we can see that carbon has gone from carbon to carbon monoxide. We're just following that single carbon atom. So we can see that that single carbon atom has gained an oxygen atom through this reaction. So we can see that carbon has gained an oxygen. So we can see that using our definition that carbon has been oxidized, and then the iron oxide species has been reduced by default because it has lost oxygen to form pure iron. So we can see that in our answer here. Okay, thank you everyone. So in the next video we're going to discuss oxidation numbers and practice assigning them to a full equation to determine whether it is actually a redox equation. So thank you for listening. See you next time.